Let's talk about the preparation of alkyl halides from alkynes. Now, if we have the alkyne means that carbon has the triple bond with it. Now, reacting with this triple bond, we could have many methods to convert it into alkyl halide. Let us say we react with HX. Now, if it is reacted with HX, then in that case we get C double bond C, and we get one side halogen and other side hydrogen. Now, if we further react it with HX, then in that case we get the hydrogen and we get the halogen. Now, the important thing about this particular reaction is that we always get a geminal dihalide. That is, the two halogens are always attached to the same carbon. So we get the geminal dihalide when the alkyne reacts with a hydrohalic acid. Now, similarly, if we talk about the reaction of an alkyne with X2 in presence of CCl4 or CS2, we get the halogen. The mechanism is the same as we have the mechanism with alkene. Another molecule of X2 react in presence of CS2 or CCl4 is going to give us the vicinal tetrahalides. This is what we call as vicinal tetrahalides. That's what we have vicinal tetrahalides. That is what we have as the reaction of alkynes to give haloalkanes. There could be lot many methods of preparation of haloalkanes. We can prepare the haloalkanes from haloalkanes, and these are called what we know as the halide exchange reaction. The halide exchange reaction. The most famous of the halide exchange reaction, the first one is called what we know as the Finkelstein reaction. When you talk about the Finkelstein reaction, this is a reaction in which Rx, now again, X, what X could be? X could be Cl, it could be Br, reacts with NaI in dry acetone as the solvent. Now, this is an equilibrium driven reaction in which we know that sodium iodide is soluble in the dry acetone because of its higher covalent character, while in the product, when sodium bromide or sodium chloride is formed, it happens to be insoluble in the acetone and therefore is precipitated. Therefore, the reaction is pushed forward due to the removal of the product, that is simple Le-Chatelier principle. We end up with Ri plus NaX, which is insoluble and is precipitated out so that the reaction keeps on moving in the forward direction. So this turns out to be the Finkelstein reaction or the halide exchange reaction. Now the second reaction that we have is what we know as the Schwarz reaction. The Schwarz reaction is the only practical method of preparation of alkyl fluoride. In this case, again, we have Rx, which could be RCl or RBr, and we react it with a heavy metal fluoride. That heavy metal fluoride could be AgF, could be Hg2F2, could be SbF3, or some other heavy metal fluoride. If we heat it, the alkyl halide with a heavy metal fluoride, it would lead to the formation of alkyl fluoride along with the heavy metal chloride or bromide. Now, in this particular reaction, this happens to be a very important reaction because any compound which contains fluorine attached to carbon, that is prepared by the Schwarz reaction. It could be the chlorofluorocarbons, it could be the Teflon. So all these compounds are prepared using the Schwarz reaction. So this is a halide exchange reaction, that is the preparation of haloalkanes from haloalkanes. Now we get along with the most important reaction of the preparation of haloalkane, and that is the preparation from alcohols. Alcohols are easily obtained natural compounds. So most of the organic compounds are produced from alcohols. Now let's talk about the reaction. We have ROH. This is the simple way to represent an alcohol. OH is the alcoholic group. ROH is reacted to give RX. Now, how do we convert ROH into RX? The X minus is not a strong enough nucleophile to replace OH minus. And further, when ROH reacts with a very strong nucleophile, or in this case a base, it is actually going to attack on H rather than O, or rather than carbon. So that is why the alcohols cannot be converted into alkyl halide by a simple substitution reaction. We have to go along with it in a different manner. When we talk about alcohol, the reaction of alcohol, then in that case, the approach is a little different. In fact, we get the opposite approach. Rather than reacting with this alcohol with a nucleophile, we react it with an electrophile. Now, let us say we talk about an electrophile as H+. Now, this particular step would be called protonation reaction. That is, we are actually converting alcohol into protonated alcohol. So we are going to get ROH2 and oxygen would be having positive. This is alkyl hydronium ion. This is alkyl hydronium ion. Now this alkyl hydronium ion would lose water. Now, if it loses water, then in that case, it's a simple reaction which we call as the dehydration reaction. This is the dehydration reaction. So we get the water removal and we get R positive. As we very well know, this R positive is what we call as a carbocation. Carbocation has a peculiar characteristic that this carbocation has a capacity to rearrange if the shift of hydrogen, alkyl, or phenyl group from the adjacent carbon is capable of giving a more stable carbocation. If it is possible, this carbocation is going to rearrange to form a more stable carbocation. So that is what we perfectly understand. So this carbocation has a capacity to react with X minus present in the system to give Rx, that is the alkyl halide. Now we need to understand what are the various reagents which are capable of providing all these three things. That is, they are capable of protonating the alcohol, they are capable of dehydrating the alcohol, and they are capable of converting the carbocation formed into the alkyl halide. So these are the various steps. The various reagent that we use, we have the first reagent, and that reagent is called the Lucas reagent. Lucas reagent is a equimolar mixture of zinc chloride with hydrochloric acid or HCl. This equimolar mixture of ZnCl2 with HCl is obtained by dissolving anhydrous zinc chloride ZnCl2 into concentrated hydrochloric acid. This is at the room temperature, that is cold. This reagent is termed as the Lucas reagent. The alcohol of 6 carbon or less are able to dissolve in the Lucas reagent to give a clear solution. When the reaction takes place, the alcohol gets converted into alkyl halide, which is insoluble in the Lucas reagent. This leads to the formation of turbidity. Turbidity can be considered to be the unclear system that we obtained when the alkyl halide is formed. It could be similar to the appearance of oil in water. So when oil is put into water, it makes the system turbid or unclear. So that is what we get as turbidity. The speed which with turbidity is obtained depends on the stability of the intermediate carbocation. More stable is the intermediate carbocation, less time it takes for the turbidity to appear. We consider the allyl alcohol, benzyl alcohol, or tertiary alcohol. The allyl, benzyl, and tertiary alcohol form allyl, benzyl, and tertiary carbocation. These carbocations are extremely stable and therefore they are formed immediately. So we can consider that if we have Lucas reagent and we add to it dropwise alcohol, then the moment the alcohol touches the Lucas reagent, it is going to give a turbidity. So that would be with the tertiary alcohol, allyl alcohol, or benzyl alcohol. Then, if we talk about the secondary alcohol, then in that case, the secondary alcohol does not give immediate turbidity. It takes 5 to 10 minutes to give the turbidity. On the other hand, if we talk about the normal primary alcohols, they do not react with Lucas reagent in under the given conditions. So, this particular reaction can be considered to be a test to distinguish between the primary, secondary, and tertiary alcohols. So we can use it as the Lucas test. Then we have a reagent which we call as the Grooves reagent. Now, Grooves reagent is a simple reagent. In fact, it is the same as the Lucas reagent, the only difference being that Lucas reagent is at the room temperature or cold, while Grooves reagent is at a higher temperature hot. So Grooves reagent is capable of reacting even with the primary alcohol because we have provided heat to it. Then we could have many other reagents. Something like we could have concentrated HBr along with, we don't need anything. We can simply have concentrated HBr along with heat. HBr is much more concentrated as compared to HCl. It is a stronger acid as compared to HCl, and it is a better dehydrating agent also as compared to HCl. So with concentrated HBr, we do not need to use ZnBr2 or something else. So concentrated HBr and heat can be used. We can use concentrated HI along with heat. Many times it is nice enough to produce the acid, the hydrohalic acid, right in the reaction mixture. For that, we could use sodium chloride along with concentrated sulfuric acid. Now, concentrated sulfuric acid is a very good protonating agent, it's a very good dehydrating agent, and in addition to that, the NaCl would be able to provide the Cl minus for the reaction to take place. So NaCl with concentrated HCl, concentrated H2SO4 along with heat also can be used to produce the haloalkane. Further, we can use NaBr along with concentrated H2SO4 and heat. That would be able to give us alkyl bromide. If we have to use sodium iodide, then in that case we do not use sulfuric acid. Sulfuric acid, in addition to being a strong acid and a strong dehydrating agent, is also a good oxidizing agent. It is a strong enough oxidizing agent to convert I minus into I2. If I minus is converted into I2, then in that case the reaction is not going to take place. So if iodine is to be used, we cannot use concentrated sulfuric acid. We use instead of that concentrated phosphoric acid. Now, phosphoric acid is a bit weaker acid as compared to sulfuric acid, but it is still a good dehydrating agent and a good protonating agent. That is why for sodium iodide, we use phosphoric acid rather than sulfuric acid. So these are the few reagents which convert the alcohol to alkyl halide going through the carbocation mechanism and, if possible, rearrangements. But there are certain other reagents as well. One of those reagents is thionyl chloride. If we have alcohol and we react with SOCl2, this SOCl2 is going to convert the alcohol into RCl along with SO2 along with HCl. The important thing about this reaction is that this does not proceed through the formation of carbocation. This particular product, the byproducts which are being formed are gases, so they are easily eliminated from the reaction mixture. That is how we are able to get relatively pure alkyl halides. Further, no carbocation is being formed in this particular reaction, so no rearrangement takes place. That also could be a useful technique. The mechanism of this reaction is a little different. Here we have the carbon, we have O, H, which reacts with SO, Cl, Cl. Now, here what happens is this oxygen shifts the electron cloud to sulfur. The sulfur chlorine bond cleaves. The chlorine attacks hydrogen, which takes away the electron, gives the electron to oxygen. So, the very first step, HCl is released out, and we get a species in which we have the oxygen attached to sulfur and another chlorine. Now, within the molecule itself, a reaction takes place, the bond cleaves, and we get Cl along with SO2. Now, this particular reaction, as such, is termed as acid-I reaction, substitution nucleophilic intramolecular, in which the chlorine attacks from the same side as the OH. Therefore, it should be having the retention of configuration. But according to NCRT, this reaction proceeds through a backside attack mechanism, which is termed as SN2 mechanism. So this should be giving an inverted product. We have to follow the NCRT. So we would also consider the inverted product, but actually the configuration retained product is formed in this particular reaction. There are certain other reagents which behave in the similar manner as the thionyl chloride. Now, SOCl2 is what we know as the thionyl chloride. Now, other reagents which are able to react in the same manner are PCl5, PCl3, PBr3, P plus Br2, or P plus I2. Now, quite obviously, PCl5 and PCl3 would be giving alkyl chloride. PBr3 or P plus Br2 would be giving alkyl bromide, while P plus I2 would be giving haloiodide, the iodoalkanes. So that's what we are going to get the products. So these are the reactions which we can use to convert alcohols into alkyl halides. Then we could have the conversion of the carbonyl compounds into alkyl halides. When we talk about the preparation of alkyl halides from the carbonyl compound, that is aldehydes and ketones, one of the simple reaction would be that if we react this aldehyde or ketone, that is a carbonyl compound, with SOCl2 or PCl5, then in that case, we are going to get a geminal dihalide, in this case chloride, along with SO2 in case of SOCl2 and POCl3 in case of PCl5. So that is what we are going to obtain in this particular reaction. But there is a very, very important reaction of the carbonyl compounds which leads to the formation of chloroform or haloforms. This particular reaction is termed as the haloform reaction. Talking about the haloform reaction, this reaction is of the methyl ketones. Now here which we have written R, it could be any alkyl group. It could even be an aryl group, or it could be hydrogen. So it could be alkyl group, aryl group, or hydrogen. If it's an alkyl group, it's a normal ketone. If it's an aryl group, it's an aromatic ketone. But if it is hydrogen, it actually turns out to be aldehyde, and that is acetaldehyde. So acetaldehyde is the only aldehyde which is capable of giving the haloform reaction. This is the reaction of the carbonyl compound which contain three alpha hydrogen on the same side on one carbon. Now here, this particular methyl ketone or methyl carbonyl compound reacts with thrice of OX minus. Now this is what we call as the hypohalite ion, not halide but halite ion. Now the question arises, what are the reagents which are capable of giving us the hypohalite ion? The hypohalite ion can be obtained by the reaction of X2 with OH minus. This leads to a disproportionation reaction in which OX minus along with X minus are produced. So this is what we have as a disproportionation reaction. For example, we could have Cl2 reacting with 2NaOH, which gives us which gives us NaOCl plus NaCl plus H2O. So this is what we have as a disproportionation reaction. This hypohalite ion is what takes part in the reaction. Here it's not a compulsion that we have to use NaOH. We could use Na2CO3. We could use something like Cl2 along with CaOH twice. Now, when Cl2 reacts with CaOH twice, then in that case it forms CaOCl2. Now, which we can write it as CaOCl and Cl. We can write it as CaOCl whole twice plus CaCl2. Now, this particular mixture, any of these reagents which we can consider, is what we know as the bleaching powder. So bleaching powder is also capable of doing this reaction. You may get on the arrow, they might write the bleaching powder. They might write calcium hydroxide along with Cl2. They can write calcium hydroxide along with I2. They can use sodium hydroxide along with I2, or they can even use sodium carbonate along with I2. We need to understand that this particular reaction takes place by the hypohalite ion, and any condition which can lead to the formation of hypohalite ion, that condition would be enough to give the haloform reaction. So bleaching powder can be used. This all the things could be used. So now, when the reaction takes place, this 3OX minus is going to attack. They are able to give us RC double bond O minus, along with twice of OH minus, along with CHX3. So that is how we get the products. Now, this particular reaction has multiple uses. The first use could be to produce the haloform, that is CHX3 can be produced by this particular reaction. The second reason could be, second use could be that we can prepare the carboxylic acid having one carbon less than the carbonyl group that we have. As you can very well see that this CH3 of the carbonyl group has converted into CHCl3 and has been removed from the alkyl group. So we get the carboxylic acid which has one carbon less than the carbonyl compound. So this can also be considered a step down or a degradation reaction. Further, when we talk about this reaction, it can also be used to identify and distinguish between the methyl ketones and non-methyl ketones, such as we can use it to distinguish between propanone, that is acetone, and propanol, that is an aldehyde. It can be used to distinguish between 2-pentanone and 3-pentanone. 2-pentanone has 3 alpha hydrogens, while 3-pentanone has only 2 alpha hydrogens on any of the sides. So that is how it can be used as haloform test. So this is what we have as haloform reaction. The detailed mechanism of haloform reaction will be done in the chapter aldehyde and ketones. So this is what we have as the haloform reaction or the preparation of the alkyl halides from carbonyl compounds. The alkyl halide can also be prepared from carboxylic acid. Now, the very first reaction that we talk about is called Hell-Volhard-Zielinski reaction, the HVZ reaction. In HVZ reaction, we have a carboxylic acid having at least one alpha hydrogen. Now, if this alpha hydrogen is reacted with X2, now X2 could be Cl2, it could be Br2, in presence of red phosphorus, we end up with X on the alpha carbon and the carboxylic acid. So we are able to get alpha halocarboxylic acids. So this is what we call as the HVZ reaction, Hell-Volhard-Zielinski reaction. Okay. Here, phosphorus is actually the red phosphorus. A simple reaction, HVZ reaction. Then we have another reaction. Let's say we have, this is called the Borodine-Hunsdaecker reaction. Normally it is written as Hunsdaecker reaction only. In case of Hunsdaecker reaction, we have a carboxylic acid. The carboxylic acid is reacted with Ag+. Now this Ag+ is normally obtained by the tolerance reagent, that is ammoniacal silver nitrate. Ammoniacal silver nitrate solution, which is termed as the tolerance reagent. Now this is able to give us RCOOAg plus minus. This is the silver carboxylate. This silver carboxylate, when it is treated with Br2 and heated, it is heated along with Br2, it gets converted into RBr along with AgBr along with CO2. Now, this is also a kind of a decarboxylation reaction. And also, the alkyl halide which is formed has one carbon less than as compared to the carboxylic acid. So, this is also a step down reaction, a degradation reaction or the step down reaction. So, this is what we call as the Borodine-Hunsdaecker reaction. Here we are going to get RBr. If in place of Br2, we are going to use I2, we have again RCOAg, and we use I2 in place of Br2. The step again is going to be the same. Ri would be obtained, Agi would be obtained, and CO2 would be obtained. But Ri is extremely reactive. This Ri has a capacity to react with the remaining silver carboxylate, and this is also capable of giving a substitution reaction in which I of the Ri is replaced by RCOO minus. So we end up with RCOOR along with another part of AgI. Now this is an ester. So if instead of Br2 we are able to use I2, then instead of alkyl halide we are going to end up with an ester. This particular reaction also has a name. It's called Birnbaum-Simonini reaction. Now this Birnbaum-Simonini reaction is not as such in your course, so you can actually ignore it. So this is the method of preparation of alkyl halides. So this is the preparation of alkyl halides from the carboxylic acids.